All right. Good morning, everyone. Everyone's had a good day. Uh, the test results have now come back, and by popular request, I've been asked to make another take-up video for test 2. So let's really quickly take a look at some of the solutions. So question 1 will evaluate this limit. Whenever we have a limit, the first thing that we should do is a direct sub. So here, if we sub in, we'll have 3 over 3 to the power of 1 over 3 minus 3. So this is 1 to the plus minus infinity. So this is an indeterminate form, so we're going to want to rewrite it using L'Hopital's rule. In particular, if we take the log, so let's do our trick here, where we'll let L equal this limit, then the ln of L will equal the ln of the limit x goes to 3 of x over 3, 1 over 3 minus x. And by the continuity of the logarithm, we can pass the logarithm through the limit. Goes to 3, and we can bring down our 1 over 3 minus x outside of the log. If we were to try a direct sub now, we are really close to being in the correct formulation here. So if we did a direct sub, now we have 1 over 3 minus 3, which is 1 over 0, and then ln of 3 over 3, so it's ln of 1. So we have plus minus infinity times 0. So what we could just do is move this down twice. So this is limit as x goes to 3 of the ln of x over 3 divided by 1 divided by 3 minus x. No, because this would be in the numerator of the function. So we need to have 1 divided by, we could actually just have 3 minus x. So now it's in the denominator. So now if we were to do a direct sub, we would have 0 over 0. So now we can try applying our L'Hopital's rule. This is the limit as x goes to 3 of, so the ln of x over 3, we're going to have 1 over x over 3, which is 3 over x, times the derivative of the inside, which is just 1/3, divided by the derivative is negative 1. Limit as x goes to 3 of negative 1 over x, which is equal to negative 1/3. So since this is the ln of L, that means L is equal to e to the negative 1/3 b. So f of x is equal to x e to the 2x. Let's find the largest interval f is concave up. So we need to take two derivatives. F prime of x is equal to, by the product rule, e to the 2x plus 2x e to the 2x. And then, nope, 2e to the 2x, excuse me. Derivative of the first term is x. Derivative of the second term is, actually, yes, we were right the first time. 2x e to the 2x. The second derivative here, f double prime of x, will now be 2e to the 2x plus 2e to the 2x plus, so that's the derivative of the x term, and now the derivative of the e to the 2x term will have 4x e to the 2x. So this is e to the 2x factored out. So we'll have 2 plus 2, which is 4, plus 4x. We want this to be greater than 0. The e to the 2x term is always bigger than 0, so this is the same thing as saying 4 plus 4x bigger than 0. So x is bigger than, so move 4 to the other side, so negative 1. So x is bigger than negative 1, so negative 1 to infinity. F of x is equal to ln of this. Find the vertical asymptotes of f. Remember, ln has a vertical asymptote. Ln of x has VA at x is equal to 0. So we want the inside equal to 0. 1 plus 2 over x equals to 0. So 2 over x equals negative 1. So x is equal to negative 2. So this is the first case. Now the other thing is we want to investigate when f blows up at a certain point. So here limit of f as x goes to -2 is going to be negative infinity. So if we were to draw that out, as x goes to -2, that f of x is going to go towards negative infinity. And now the question is, okay, what is the other vertical asymptote? Now, in particular, the other solution that we could have is if x is equal to 0, then this denominator is going to shoot up. So as x goes to 0, then 2 over x goes to plus minus infinity. And in particular, if x goes to 0 from the right-hand side, so if we're going to positive infinity, then ln of, so then 1 plus 2 over x goes to positive infinity. So then ln 1 plus 2 over x goes to positive infinity because ln is unbounded as the input goes to infinity. So then our asymptotes are going to be at -2 and at 0. Find the horizontal asymptotes of f. So we have to check the two limits at infinity and at negative infinity. So a limit as x goes to infinity of 1 over 2 minus e to the negative 3x. First thing we should always try is a direct sub. So this is 1 over 2 minus e to the negative infinity. But e to the negative infinity, that just approaches 0. That's 1/2. If we were to try limit as x goes to negative infinity now, this is 1 over 2 minus e to the negative 3x. By a direct sub, 1 over 2 minus e to the positive infinity. So we're dividing by this super large number, which is in the negative. So we're going to be approaching 0 from the bottom. So, well, this is just going to give us 0. So y is equal to 0 and y is equal to 1/2. So d. The graph of the derivative is shown below. At what values of x does f have a local maximum? So remember, the f prime gives us this accumulation, the change. So in particular, we're going to want to keep going and accumulate as much positive change as we can. So here we're accumulating negative change. Here, every time we have a 0 of f prime, or when f prime doesn't exist, that's a possible candidate. So this is a possible candidate. But you'll see, since we've accumulated so much negative area, this is definitely not going to be a max of f. So we'll keep going along. Here, at this cusp, the derivative, oh, actually, no, it still exists. Even though there's a cusp here, the first derivative still exists, just the second derivative does not. So we'll keep going along. We have another 0 at 4. Notice we've accumulated a bunch of positive area, so this is a possible candidate here, but we'll keep going. Here we'll go along. We reach this value at 5, another 0, but we've accumulated negative area. So f of 5 is going to be less than f of 4, and f of 4 is going to be bigger than f of 1. Those are each of the possible candidates, so it looks like we're going to have a local maximum at 4 only. The graph of the derivative f of a function, or the derivative f prime of a function f is shown below. Calculate this limit. First thing you always try when you have a limit is a direct sub. So if we do a direct sub, this is going to be f prime at 7 over 2 times 7 minus 7. So f prime at 7, well, let's look. What's f prime at 7? Oh, that's 0. So we have 0 over 0. Notice, remember, we're graphing f prime. They're giving us f prime here. So that doesn't work. So we have 0 over 0. So let's try a L'Hopital's rule. In this case, this is limit as x goes to 7 of f double prime at 7 over derivative of x minus 7 is just 1. So 2 times 1, which is 2. F double prime at 7, that's just the derivative at 7, which you can see the slope of this line is -1. As we move to the right 1, we go down 1. So the slope is -1. So this is -1 over 2. Don't drop the limit sign, which is just -1/2. farmer has 24 meters of fencing for enclosing a trapezoidal field along a river. One of the parallel sides is 3 times longer than the other. No fence is needed along the river. Find the largest area the farmer can enclose. So the area of this trapezoid is going to be, so let's see. Yeah, the area of this trapezoid is going to be, let's call this, let's call this y. So the restriction, the constraint for this is that 24 must be equal to the total perimeter that we have to put a fence along. So it's going to be 3x plus y. And also the area, so now the objective function, the area, which is a function of x and y, is going to be the average of these two lengths. So think from the trapezoidal rule. So 3x plus x over 2 times y. So in particular, we can isolate for this side for y. So y is 24 minus 4x. And we can move this all the way over here. This gives us 4x over 2, so 2x times 24 minus 4x. Notice if x is equal to 0 or if y is equal to 0, then we have minima. So x is equal to 0 or y is equal to 0 give minima. And if we're looking for a maximum, then in that case, let's just find the critical points of a. A of x. So to find the critical numbers, let's take the derivative. A prime of x is equal to 2 times 24 minus 4x plus 2x times negative 4. And we want this to be equal to 0. Notice that this is never going to be undefined because we're taking a derivative of a polynomial function. 48 minus 8x minus 8x is equal to 0. This is negative 16x, so x is equal to 3. So if we want to find the largest area that we can enclose, well, we can just sub this back into our area function. So a at 3 is equal to 2 times 3 times 24 minus 12. So 6 times 12. So 6 times 12 is 72. Evaluate the following limit. So this looks like a telescoping sum. We have cancellations between terms. So let's just keep the limit on the outside and write out the first couple terms of the sum. So we have 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus the final terms of our sum. We have, let's do n minus 1 first. So 1 over n minus 1 minus 1 over n plus 1 plus 1 over n minus 1 over n plus 2. So all of these middle terms are going to cancel. The 1/3 will cancel with a hidden 1/3. 1/2 will cancel up until, oh no, the 1/2 won't cancel with anything. And then we're going to be left with an extra 1 over n plus 1 and then 1 over n plus 2. So those are both going to go away because, well, let's just show this really quick. So we have limit as n goes to infinity of 1 over 1 plus 1 over 2 minus 1 over n plus 1 minus 1 over n plus 2. As n goes to infinity, these both go to 1 over infinity, which is 0. So 1 plus 1/2 plus 0, which is 3/2. We'll evaluate this limit by expressing it as a definite integral. So this is a pretty nice hint that they gave us. So in particular, here, if we see this is like our function evaluation, this is going to tell us that, well, this one here is going to tell us the a point. So if we're setting up the integral from a to b of f of x dx, we can choose a is equal to 1. In that case, this 2i over n, this can give us our b minus a over n. So if we set b equals to 3, then b minus a is 2. Then also here we see our b minus a over n. So all that's needed is to define our function f. So we could say f of x is equal to the reciprocal. So we could say it's 1 over x squared. and then we would be plugging in our a plus our b minus a over n times 1, taking this limit. So we're integrating from 1 to 3 of x to the negative 2 dx. So this is x to the negative 1 minus from 1 to 3. So this is negative 1/3 plus 1, so 2/3. We'll let f be the function as shown below, which is a possible graph of the antiderivative. So remember, if we're looking for the antiderivative of f, then let's call the antiderivative, let's call this capital F, and in this case, the graph that's plotted is capital F prime. So the zeros of capital F prime here, so at 1/2, at a bit more than 2, at 4, and at 5.5, those have to be horizontal tangents of f. So notice here we only have 2 horizontal tangents. In A, we only have 2 horizontal tangents. In B, we have 1, 2, 3, 4, 5. So B cannot be a possibility because we have 1, 2, 3. Oh, no, we only have 4 in this one. So B is a possibility. C, we have 1, 2, 3, 4. That's also a possibility. D, we only have 2. So D cannot be. In E, we have 1, 2, 3, 4. Okay, so now let's start looking a little bit more at the specifics. So we have our first horizontal tangent should happen at about 0.5. So B is a possible candidate, C is a possible candidate, but E is not because 1.5 does not work. So now, let's see, the second one happens at about 2, that one lines up. The third one happens at about 4, and then the last one happens at a bit more than 5. So both B and C are possibilities here. So maybe let's try and take a look at this end behavior. So at 0, our derivative should be positive. Or sorry, at 0, our derivative is negative. So our function should have negative slope. So here we have positive slope, and we have negative slope here. So B has to be our answer, because C, the slope is pointing in the wrong direction. We should have negative slope. If f is equal to secant squared plus secant x tan x, f of 0 is 0, find f pi over 4. So f of x is equal to integral of secant squared of x plus secant x tan x dx, which is equal to tan of x plus secant of x plus c. Then in that case, f of 0 is equal to tan at 0 plus secant of 0 plus c. We're given that that's 0. Tan of 0 is 0. Secant of 0 is 1. So that means that moving to the other side, c must be negative 1. So in that case, f of pi over 4 will be tan of pi over 4 plus secant of pi over 4 minus 1. So here, this tan of pi over 4 is 1, so these two cancel. Secant of pi over 4, that's 1 over cosine of pi over 4. Cosine of pi over 4 is root 2 over 2, or 1 over root 2, so our final answer is just going to be root 2. So C. If f of 1 is 3, f of 3 is 7, evaluate this integral. So, so let's let u equal 1 plus f of x, and we see the derivative of u up in the numerator. So if we let u is equal to 1 plus f of x dx, we'll let du equal to f prime of x dx. So here's the numerator. In that case, our integral I becomes the integral of, also let's change the bounds. So u at 1, when x is equal to 1, will be 1 plus f at 1, which is equal to 1 plus 3, which is 4. And u at 3 is equal to 1 plus f at 3, which is equal to 1 plus 7, which is 8. So the integral from 4 up to 8 du of 1 over u. So this is the log absolute value of u evaluated from 4 to 8, which is from the fundamental theorem 2. So this is equal to the ln of 8 minus the ln of 4. Okay, so this is equal to ln of 2 to the 3. So 3 ln of 2 minus ln of 2 to the 2. So 2 ln of 2, which is equal to ln of 2. A. Find the value of the following sum. We can do this one by breaking this up into different parts. So this is the sum from I is equal to 1 up to n of 1 plus 2 times the sum from I is equal to 1 up to n of I. The first one is just n copies of the number 1. And then the second one, we can use our Gauss's trick. So this is n times n plus 1 over 2. So these 2's cancel. So this is n plus n times n plus 1. So we can factor this. This is n times 1 plus n plus 1. So this is n times n plus 2. We'll let f of x be arctan of x. Find the value of c that satisfies the conclusion of the mean value theorem on the interval 0, 1. So remember what the mean value theorem says. There is a c on 0, 1 such that f prime at c is equal to, f prime at c we'll call it because we need a good notation for it. Arctan of 1 minus arctan of 0 over 1 minus 0. This is the average slope. Arctan of 1 is pi over 4. Arctan of 0 is 0. And over 1. So this is just pi over 4. Now f prime of c is the derivative of arctan. Remember, derivative of arctan is just 1 over 1 plus x squared. So evaluated at c is 1 plus c squared. So we can multiply on both sides. So 1 plus c squared is equal to 4 over pi. So c squared is equal to 4 over pi minus 1. So c is plus or minus 4 over pi minus 1. And then the final question is to say, okay, how can we evaluate which one of these is correct? Well, we can just take the principal argument. So let's just take the positive version. So here we can choose c 4 over pi minus 1. We'll evaluate the following using the properties of the integral and relating it to areas. So we're integrating from 0 to 4. So let's draw up this region, 0 to 4. Absolute value of x minus 1 plus 4 over pi times the square root of 16 minus x squared dx. So let's break these up into two integrals. So this is the integral from 0 to 4, the square root, or the absolute value of x minus 1 dx, plus 4 over pi times the integral from 0 to 4, root of 16 minus x squared dx. This first one, there's going to be two triangles. Let's actually break this drawing up into two smaller ones. So here's from 0 to 4. Our x minus 1 will have a cusp here. It'll go up a distance of 1. This triangle has length 1, 1. There's 3. This triangle has a length of 3. So the integral under this region from 0 to 4 will just be 1/2 of 1 times 1 plus 1/2 of 3 times 3. This second integral will be 4 over pi times the area from 0 to 4 of the semicircle. Remember, if we have y is equal to 16 minus x squared all rooted, then that means that x squared plus y squared is equal to 4 squared. This is a circle of radius 4. So if we're integrating from 0 up to 4, this is a semicircle here. Excuse my terrible drawing for a circle. This is radius 4 as well. So it's a stretched circle. So it's a quarter of the circle. So 1/4 times pi times 4 squared, because that's the radius of the circle. So these two 4's cancel, the pi's cancel. So we have 16. So let's bring this calculation down. This is 1/2 plus 9/2, so 10/2. 5 plus 16, which is 21. We'll let f be the graph shown below. G is the integral. Which of the following statements is true? So g of 8 is negative, g of 6 is bigger than g of 9, and g is concave down onto 8. Okay, so let's start with this one. G of 8 is negative. So what is g of 8? G of 8 is the integral from 0 to 8 of f of t dt. So this is f of t right here. So is the area from 0 up to 8 negative? Well, 8 is right here. And you'll notice that all of this positive area that's accumulated, this is much larger than this negative area here. So g of 8 is actually going to be positive. So this is not correct. So question 2 says, is g of 6 greater than g of 9? G of 6 will be right here. We'll have a ton of positive area accumulated. G of 9 will have accumulated negative area up to this point. So g of 6 is going to be greater than g of 9. So yeah, 2 is correct. G is concave down on 2, 8. So in order to find g, what the concavity of g, we need to check the second derivative. So g prime of x, we'll find the first derivative. That's the derivative of integral from 0 to x of f of t dt. By the fundamental theorem number 1, this is just f of x. So g double prime at x is going to be f prime at x. So on the interval 2 to 8, you'll notice that f prime of x is negative. So g double prime is negative, so g is concave down. So yes. So 2 and 3 are correct. We'll let g be given here. Let's find g prime at 0. So in order to find g prime at a point, let's first find g prime. So g prime is equal to derivative of integral from 2 to 3x root of t cubed plus 16 dt. Let's let f of t be equal to this root of the inside. And in that case, we'll let f be the antiderivative. The reason why is because by the fundamental theorem of calculus, this is equal to f of 3x minus capital F of 2, so both capital. So this is by fundamental theorem 2. The reason why we're doing this is because when we take this derivative, we're going to get an extra chain rule out of it. And then the derivative of this constant is 0. So if we just tried to apply fundamental theorem 1, we would have lost this constant. So now this is equal to 3 times f of 3x. So f of 3x is going to be the root of 3x cubed plus 16. G prime at 0 is 3 root of 0 plus 16. 3 times 4, which is 12. We'll let f be the graph who's shown below. Estimate the value of c that satisfies the conclusion of the mean value theorem on the interval 0 to 5. So here's our interval beginning at 0 and our interval beginning at 5. Here, f at 5, let's say, is approximately 2.6. This is the conclusion of the mean value theorem. Equals f prime at c for some value c. So f of 5 is approximately 2.6. F of 0 is approximately like, oh no, not 2.6, maybe like 2.8 or so. f of 2 is approximately 2.5 divided by 5. So maybe let's say 2.75 for good measure, so we have divisibility by 5. So this is now 0.25 over 5, so it's equal to 0.05 is equal to f prime at c. So let's find some point which has approximately this average slope. Maybe it looks like approximately the point 3.25 has that slope. If we were to draw the slope anywhere else, so for example at 2.5 this is negative, so it couldn't be. At 1.25 we have a negative slope, so it couldn't be. 1.75 we still have a negative slope, couldn't be. And at 4.5 this slope is much too large. We'll consider the function whose graph is below. We'll estimate the integral using 3 rectangles and right endpoints. So this interval is of length 9. So 7 minus negative 2 is equal to 9. So if we use 3 rectangles, each width has to be 3. For right endpoints, so here's number 1, here's number 2, and here's number 3. It goes up just to 7. So the integral is going to be approximately the width times height. So the height will be f of 1 plus the height at 4 is f of 4 plus f at 7. So this is 3 times f of 1 is negative 3, f of 4 is positive 3, f of 7 is 0. So 3 minus 3 plus 0, this is going to be 0. 0. B. Find the total area enclosed by the curves y is equal to x squared, y is equal to x, and x is equal to 2. So first thing that we're going to want to do is plot out these curves. X squared is going to look like this. X is going to look like this. They intersect here at 1, but they're going to keep going onwards. And this is like the least to scale drawing ever, but it's going to end at 2, 4, and it's going to end at 2, 2. So we want to find the area here and the area here. So the total area is going to be the integral from 0 up to 2, the absolute value of x squared minus x dx. We want the absolute value of the areas between them. Now, unfortunately, it's very difficult to solve this integral analytically. So what we should do is notice that we have this one intersection point at 1 and break up the integral such that the positive one always lays on top. So this is the integral from 0 to 1 of x minus x squared dx plus the integral from 1 to 2 of x squared minus x dx. X squared is on top, past 1. So we can solve this by the fundamental theorem. This will be 1/2 x squared minus 1/3 x cubed, evaluated from 0 to 1, plus 1/3 x cubed minus 1/2 x squared, evaluated from 1 to 2. So this will be 1/2 minus 1/3, and the 0 contributes nothing. Plus, this will be 1/3 times 8 minus 1/2 times 4 minus 1/3 plus 1/2. So 1/6 plus 8/3 minus 2 plus 1/6. So this is, this becomes 1/3 plus 16 8/3, so 9/3. So 3 minus 2, which is equal to 1. All right. So that is the midterm. I hope this helps clear up any questions that you might have. And yeah, we'll see you Friday.